In this video, we are going to be discussing Intext question 2.9. It is given after the whole osmotic pressure and osmosis in your textbook. So let's start. Vapor pressure of pure water at 298 Kelvin is 23.8 mmHg. 50 grams of urea is dissolved in 850 grams of water. Calculate the vapor pressure of water, so vapor pressure of water for the solution, and the relative lowering. So we're obviously using the relative lowering of vapor pressure for this particular question. So we are going to assume that our solvent, that is water, is denoted as 1 and urea is denoted as 2. Okay, water is 1, urea is 2. Let's write down what's given. So first of all, mass of, so W2, that is the mass of urea, is 50 grams. We've been given mass of water, which is 850 grams. We've been given the vapor pressure of pure solvent, that is P1 naught, will be equal to 23.8 mmHg, which is millimeters of mercury. So P1 naught equals to 23.8 mmHg. Now we need to calculate the vapor pressure, right? So the first of all, let's also write down the equation for relative lowering of vapor pressure. So according to relative lowering of vapor pressure, we got the final equation as P1 naught minus P1 whole divided by P1 naught equal to X2. Okay, so X2 is a mole fraction of our solute. And then we can easily just say that the mole fraction of solute is going to be equal to the relative lowering of vapor pressure, because that is what the whole thing, this whole thing represents. Okay, and then you can use this to calculate the value of P1. Okay, when you saw this question, you might have wondered, oh wait, we need to do the calculation for the vapor pressure of water first. But to do that, you actually need to calculate the mole fraction, and then that in turn is equal to the relative lowering of vapor pressure. And using this equation, we can calculate the value of P1, or the vapor pressure of water for this solution. So let's start with mole fraction. So mole fraction equals to, so X2 will be equal to the number of moles of 2 divided by the number of moles of 1 plus number of moles of 2. So again, we need to calculate the number of moles of 1 and 2. But before we do that, we need to calculate the molar mass of 1 and 2. So molar mass of water, that is good, I'll refer to it as M1, that's molar mass of water, will be equal to 2 into 1 plus 16. So that's equal to 18 grams per mole. This is a mole fraction of water. The next one is going to be equal to M2, which is the mole fraction of urea. If you want, you can write down the formula and just count. So NH2CO NH2, that's the formula. So you have 2 nitrogen atoms. So that means you have 2 into 14 plus 1 carbon atom, so just say 12, plus 1 oxygen atom, which is 16, plus 4 hydrogen atoms. So 4 into 1. So this in total is going to give us 60 grams per mole. Okay, so next we will calculate the number of moles of 1 and 2. Number of moles equals to mass divided by molar mass. So mass has been given to us. This is 850 grams of water. So 850 grams divided by 18 grams per mole. That is equal to 47.22. So again, we can cancel this and we get 47.22 moles. Or yeah, 47.222 moles. I guess. N2 will be equal to 60, oh sorry, 250 grams of urea, so 50 mass divided by molar mass, so 60 grams per mole. Gram gets cancelled, and then you get 0.833. And we only care about the value of x2, right? We don't need the mole fraction of water. So just going to do the calculation for mole fraction of urea. So x2 equals to the number of moles of 2, which is 0.833, forgot to write the units, moles divided by 47.222 moles plus 0.833 moles. And this is equal to I just realized I calculated this the different way. Essentially, what I did was I calculated the mole fraction um, of water and then subtracted it with 1. You can do it that way as well. That's perfectly fine. And I decided I'd do it this way for the video. So 47.222 plus 0.833 equals to 48.005. So you have 0.833 divided by 48.055. So 0.833 divided by, and yes, I am calculating it in parallel because I did not learn how to pause the video while recording. So yeah, so we get this when simplified, and yes, the moles can get cancelled, and that's why I didn't bother writing it over here. So you get 0.0173 as the mole fraction of urea. So this is the mole fraction of urea, and this is equal to the relative lowering of vapor pressure. So the relative lowering of vapor pressure equals to 0.0173. Okay, so that's the relative lowering of vapor pressure. Next, let's calculate the value of P1. So we know the value of P1 naught. It's been given to us, and that is 23 mmHg. We have the relative lowering of vapor pressure, the mole fraction of B. So you can just substitute it into this equation and calculate. So essentially, you're going to get 23.8 mmHg minus P1 whole divided by 23.8 mmHg is equal to 0.0173. So this, obviously I'm going to be simplifying it for us. So 23.88 mmHg, we're going to be stuck with that unit because the final answer has the same unit. So you get 0.4141 mmHg, and then minus P1 will be equal to 0.4141 mmHg minus 23.8 mmHg. And then this gives us P1 minus P1 equals to minus 23.3859 mmHg. And then obviously this and this gets cancelled. So this is going to be the vapor pressure of water in the solution is 23.3859 mmHg. So essentially, we use the relative lowering of vapor pressure equation to calculate the relative lowering. Using the mole fraction, we basically calculated the mole fraction of the solute. And then from there, we were able to calculate the vapor pressure of the solvent in solution. With that, we're done with this video. In the next one, we're going to be discussing Intext question 2.10.